Good day, ladies and gentlemen. This is the 13th lecture of the series of lectures describing the RM software for filter design. We'll speak now about Parallel Activr RC circuit or filter synthesis. Here is the overview or the contents. After the introduction, we will speak about the decomposition of the transfer function into a form of a sum of partial fractions that will allow for parallelization. Then we will describe the process of parallel synthesis, including the cells which will be used. Finally, we will be giving a synthesis example. There are some apparent advantages of the parallel synthesis of active RC circuits as compared with the solution taking the form of cascade connection of cells. First, there is no amplification of the noise generated by the cells, especially input cells, since there is no cascade, which in case of higher order filters may become prohibitive. This issue is further elevated if the shape of the amplitude characteristics of the cells used in parallel synthesis is taken into account. Namely, both the second order and the first order cell are never high pass, which means the noise bandwidth is limited even when high pass filters as a whole are to be synthesized. Then there is no need for pole zero pairing in order to reduce nonlinear distortions and noise, since, as we will be seeing below, only poles and residues are used. In addition, there is no need for making order during extractions of the cells and consequently for assigning specific gain values to the cells in order to keep the signals within the prescribed limits. Furthermore, when parallel, in case of low pass, band pass, and all pass filters, there is no amplification of the input DC offset. Finally, when using parallel synthesis, the types of transfer functions of the cells is reduced to two, one for the first order cell and another for the second order cell, which has two variants, low and high. When the realization of the cell is sought, the later one may take two forms, low and high, which altogether is incomparably smaller in number of possible variants than in the case of cascade synthesis, which is very convenient for programming point of view. Furthermore, one may choose all capacitances in the filter to be equal, which is a unique advantage. The price paid for all these advantages is the cost of the additional circuitry needed to perform the summing at the output of the filter. Now we will say several words about the decomposition of the transfer function in the form of a sum of partial fractions. Here is, on the left side, is the factored form, and on the right side is a sum of partial fractions. The notation is as such, so that A0 is the nominal gain, N is the order of the filter, while S is the complex frequency. Z is the vector of the zeros of length M. M is the order of the numerator polynomial. To accomplish this type of a synthesis, one has first to represent the transfer function in a form of sum of partial fractions, or to find the residues as above. Here P is vector of poles and R is vector of residues. After some manipulations, the transfer function represented in a form of sum of fractions may be rearranged to a sum of bigquads, which may, in the case of odd order of the filter, have one additional first order cell as shown on the right hand side. The overall structure of the parallel realization is depicted here, and one can see that there are cells enumerated from 1 to T. T is here shown to have a value half of M plus 0.5. And there is an additional cell enumerated 0, which will be present as a short circuit in the case when the order of the numerator and the denominator are equal. As mentioned, two second-order cells are used, high Q and low Q tau-Thomas bigquad cells, which are realizing a real zero, since, as we could see in the previous slide, the zero of the bigquad cells, the numerator of the bigquad cell is first order with a real zero, which may belong to the left on the right-hand side of the complex frequency plane, which is possible to realize with this type. This is the first order cell, which will be necessary if the order of the filter is odd, and that is all. Here is the schematic of the summing amplifier. On the top is here shown the short circuit, the auxiliary path when the order of the numerator and denominator are equal. This will be absent if that is not the case. So this is the case only in high-pass filters and band-stop filters. Then there are two inputs to the summing amplifier, two sets of inputs. The first one is related to the cells which are inverting the signals. So if inversion is performed in the previous phase, then we have to restore the sign of the signal, and this is why we are bringing these signals to this inverter, summing inverter. And in the case when no inversion was performed, we are bringing the signals directly to the summing amplifier. As one could see, the synthesis of parallel filters, active RC filters, is a very simple process. The only step which is to be taken is calculating the residues, which is a simple one, and which is in generally necessary for time domain analysis. And we have not much to say except that there is a limitation in the in the RM software, or better to say, in the RC Parallel software, which use program which use here, which means only first order poles are manipulated. One cannot manipulate second order poles, which is an extremely rare situation to have poles of higher order. There are zeros of higher order, but that is not an obstacle here. Now we will go for an example. The example here is a 7th order low-pass half-band filter with 3 multiple transmission zeros. The cutoff frequency is chosen to be 73 kHz with a maximum passband attenuation of 3 dB and the minimum stopband attenuation of 40 dB. This is the cell which was used. Nice. Here is the part of the report. It is slightly edited to reduce the number of figures to accommodate to the shape of the slide. And this is the second cell. And this is the third. All 3 cells have the same structure as shown above. And then we have one first order cell, and here are the element values of this cell. That will be the complete schematic. Comes the summing amplifier. We have on the right hand side the schematic of the summing amplifier for the notation, the values of the resistors, including the inverting terminals. And as an example, these multiple zeros can be recognized here, and all 3 zeros are the same location, so we have a wide gap of the attenuation around 100 kilohertz, but nevertheless the passband is at 73 kilohertz, and here is the inlet, which is showing that where is the cutoff frequency. This is the passband in the passband, and there is no need for much elaborating this example. That will be, in fact, all for the parallel active RC circuit or filter synthesis. Thank you very much for your attention.